Hello, welcome everyone. My name is Massimiliano Manfren, and I'm going to present the work we did for the paper Normalization of Measured Energy Consumption to inform both design and operational decisions. And the work was done by me together with my co-authors Giorgia Marenzi, Lavinia Tagliabue, Giuseppe di Giuda, and Marta Boscariol from Politecnico di Milano and University of Turin. First of all, a bit of introduction. There are today many ongoing initiatives at the EU level involving energy and buildings, and in particular the European Green Deal, Renovation Wave, the new Energy Performance of Buildings Directive, the new European Bauhaus, and Repower EU, among others. All these initiatives tackle both new buildings and existing buildings, which represent the largest quota. And of course, for existing buildings, if we want to achieve an adequate level of performance to get deep decarbonization, we need to go for a deep retrofit. So we need to design solutions that are quite effective in decarbonization. And unfortunately, for existing building, we have to be able to define some very good baseline model, being able to capture the performance of the existing building. And this performance has variability that is determined by the intrinsic building characteristics, as you saw, but also on the behavior of the people. And this variability of performance can lead to a mismatch between the simulated and the measured performance, which is reported quite often in literature with the term performance gap. The primary objective of the study is the digitalization of a portion of the building stock of the municipality of Melzo, and as you can see, the title is quite long, but it's informative modeling of real estate assets for the sake of strategic planning and retrofit interventions. And the project involved first surveying buildings, then a verification of the building against current legislative requirements, the creation of BIM models, building information models that could work as a digital archive. And then on top of this work of data collection and creation of BIM, the development of simplified but validated with dynamic simulation models for energy performance calculation that are used to target rate of intervention and connected to an economic analysis of the costs. Overall, the research involved 21 buildings with a variety of end uses like schools, libraries, town halls, theaters, public centers, sports centers, and so on. In this case, we limit the analysis to a group of 10 buildings, but representing different types of end uses. And the digitalization in our case has the goal to provide some useful analytics regarding energy consumption and costs, so something that can be used operatively to take decisions regarding the future of these buildings in terms of retrofit. And in order to define the appropriate level of detailed of models to be considering constraints in terms of time, effort, and costs, we did this sort of iterative work using both data-driven sort of statistical methods and more conventional simulation tools. The case studies presented in this case are 10 buildings that you can see here on the right. So they are buildings like sport facilities, catering, public spaces, education, and they have a quite significant variability in terms of size. What has been done first is creating building information models of these buildings, and then leveraging the data from building information models, we created different type of energy models which were calibrated, which were fitted essentially to the real condition, considering 3 years of operational energy consumption data, which led to the definition, which were used for the definition of the baseline models. In terms of technical standardization for building performance simulation and particular building energy modeling today, the framework that we refer to is the ISO 52000, which is quite complete and well structured. And in particular, in terms of structure, it considers different assessment boundaries that you can see here represented. So the internal, just simple thermal balance of the building, or the balance with respect to technical system, building services, and considers also different perimeters for the analysis of, for example, the carbon emission factors or the primary energy factors of the energy carriers that are used in the buildings. And these are flagged here as with this red line. So we have a perimeter that is on site, nearby, or distance. So while the framework is well structured, we have still the problem of dealing with the performance gap because of the variability of the energy performance in actual operation of the buildings. And the only way to do it with some, in a sensible way, is to be able to track performance in time. Of course, in the case of existing building, we know that the building have been operated for quite some time, and we can record their energy consumption over a certain period of time. In our case, we consider 3 years. This approach is explained in multiple forms in different standards related to energy management and measurement and verification. You see some examples here. But the fundamental idea on which we base our work is the fact that we train the model on a certain period. The baseline period for us are the previous 3 years of operation, and then we use them in a reporting period. So from now to the future to see what's, for example, what happens if we apply an efficiency measure and if the efficiency measure corresponds to what we expect. The way to do it from a practical point of view for buildings is to take the energy consumption, calculate the energy signature, which is the average power between two successive records, and plot it against the external average temperature. And in this case, you see an example of a piecewise linear behavior where we have a base power, so a sort of base load that is normally associated with hot water usage, and the one that is temperature dependent, that is normally associated with heating. If the regression models are within these boundaries that are defined by these statistical indicators, normalized mean bias error and the coefficient of variation of root mean square error, then we can say that these models are calibrated. These models, the models based on piecewise linear regression using energy signature, are quite similar in principle, even though the formulation is slightly different, to a variable-based degree-days approach, where instead of using the energy signature, we have the energy usage, and similarly the outdoor air temperature called ambient temperature. In this case, the model that I showed in the previous slide is quite similar to this one, the 3-parameter heating model, which is reported in ASHRAE 14, which is recalled then in other guidelines and standards for measurement and verification. In our case, we take that formulation and we made a small change using, instead of using the conventional piecewise linear formulation, we used dummy variables to manipulate the formula and create the piecewise linear shape, and we compared with one slight variation of the concept using an additional dummy variable to understand if there is a seasonal change in performance. Not dependent on the temperature, but just on the period of the time, and we use it and we modeled it in this way. In practice, this is just shifting up and down the regression line for the different months. So we wanted to understand if there is a dependency on months or not. And this part represents this upper part of the modeling workflow, the one related to statistical data-driven methods. The one on the bottom represents the work done for the building energy simulation, which is being done instead with some simulation tools calibrated themselves on real data. In terms of data representation, it's quite difficult from a certain point of view to present in a very compact way the results for different for buildings that have different sizes and that have different end uses and characteristics. So the idea that we developed is the one of using something that's, in terms of visualization, that removes partially at least the temperature dependence, the time dependence, sorry. So we have energy signature, which is an average power, so is energy divided by time in the interval that we consider, in this case monthly. Size, the gross volume of the buildings that was reported at the beginning, and we represented them graphically as a function of end use to understand if there are some sort of consistent pattern. But we can clearly see that there is a linear trend, but it's not quite clear if there is a pattern dependent on end use. And of course, the dimension that remains fundamentally to be developed is the weather normalization, so the normalization with respect to outdoor air temperature that we do using the regression models. And how do they look like? In terms of model calibration, a simple regression model, so you see here all these ones are basically straight lines, can achieve calibration in 6 out of 10 buildings. So that we have some buildings that don't reach calibration. So they are not the models that don't look too bad in terms of performance with respect to the statistical indicators, but still not calibrated. This one is a bit at the border because it's 15. So what we did is to test the other type of model, the regression model type 2, where we have additional dummy variables for the monthly behavior. In this case, the performance changes slightly, so we have one more building that is calibrated. We still have these public buildings that have the public spaces, the sport facilities, and this catering building that have a behavior that is difficult to reproduce with this simple model. So probably we will need to do some further more in detail measures because they have maybe a behavior that is quite variable in time, and we cannot capture it with this simple model. Anyway, with a simple, not very sophisticated model, we are able to calibrate 7 out of 10 buildings. So if we take this calibrated model and we compute them with, so we compute the output in terms of annual heating consumption with a typical meteorological year, this is what we would normally do for if we have to simulate the building behavior for code compliance, we get at the end very, very similar results. So this is the results achieved by simulation, the more detailed calibrated simulation, and the ones by type 2 and type 1 models, and you see that there is maximum a relatively small difference, maximum 20% in all the cases, except for building 2, which was one of the uncalibrated ones. Then, if we take regression model type 1 and we train it on simulated data, we can potentially leverage this to simplify the calibration process of more detailed models, and this is an aspect that we will explore going forward as a way to simplify the workflow. And as you can see here, the model type 1, since simulated data are more regular than real data, more let's say less noisy, it is quite easy to get a calibrated line to be used as a reference in the development of the calibrated simulation. And in this case, you can see also that the data, the simulated data are quite more clustered. So it means that the conditions that are defined, for example, normally in handbooks or guidelines for dynamic simulation, are more narrow in terms of data variability compared to real data. Finally, in terms of summary of results, we have the regression models type 1 and 2 can give us a decent performance estimate comparable to the one on the dynamic simulation, but of course they are much simpler and inexpensive. So it would be nice to use them as a preliminary approach before doing the more detailed simulation. They are interpretable, so it can be easy for humans to understand what is a change in output given a change in input or parameters, and this is substantially different from more sophisticated data-driven methods. So they are easy, and they can use in the form of meta models on simulated data. So we can train them on simulated data, and leveraging the approximated physical interpretation, we can use them in an integrated way to be able to calibrate model progressively. Finally, in terms of conclusion, we can say that the most important outcomes of the research are that interpretable regression-based approaches using energy and outdoor temperature can reach calibration in most of the cases and are simple and effective, and they can leverage substantially inexpensive data, so monthly energy data and outdoor temperatures. The further work that we intend to pursue in this direction is related to the exploration of the scalability of the techniques from monthly, daily to daily and hourly data. This has already been done in other case studies, so we can extend this also to this case. And to use further development of visualization technique to enhance the applicability to building stock, where we have different end uses and sizes. And these aspects can be leveraged in the short term for just pure energy management, because we create some baseline models for the sake of energy management and measurement and verification. But then also they can inform more sophisticated decision-making processes regarding retrofit intervention of buildings. So thanks very much for your attention.